What's up, YouTubers? Jose Quiñones, the CNC Dude here. Hey, a few months ago my wife tells me that she wants to go to the Burlington Coat Factory. You know, shopping, not my favorite thing, but this place happens to have a Hobbytown USA right there, so I just basically told my wife, sweetie, take your time, no rush, you don't want to have a heart attack, take your time. I'm gonna go to Hobbytown USA. Some time goes by, she walks empty-handed at me. Whammo! I walk out with an RC car. Awesomeness. Now, in my defense, I acquired this car for my kid. And I'm not talking about my inner child, I'm talking about actually my 8-year-old son. Intriguingly, however, for the upcoming weeks, it is me doing most of the running with the RC car, so I felt kind of guilty. Went online, checked out the Craigslist, found a nice / used, good condition, fairly priced. I got it. So now I'm racing with my kid. It is a lot of fun, but still I feel this emptiness on my chest. It's like something is missing. And you know what it was? Running RC cars is a lot of fun, but what is truly fun is to change them up and put your own stuff in it. So on today's video, we're gonna see how I modified the RC car with my own set of electronics to control the motor. And not that it's doing anything incredibly different than what it was doing before, but hey, we did it because we can. It's fun, and it's my own electronics. Let's take a look. I'm gonna do a quick introduction to the electronics of an RC car. Be aware that if you're an RC enthusiast, you will want to skip ahead because you already know this. If you don't know it though, feel free to take a look. Inside of the RC car, we're gonna find a series of blocks that are in charge of controlling the motion of the vehicle. I must tell you, however, that these blocks look like this on any hobby grade RC car. However, if you go to Walmart or Target or one of those consumer stores and get one of those wimpy toy-like RC cars that are like maybe $30, $40, $50, they're probably not gonna look like this. This is the structure of an RC car in the hobby grade, anything over $100 up to $1,000. There are many brands out there. The ones that I know of are Trax and Losi, but I bet there are others. What are the blocks in question? Well, we're gonna need a receiver. The receiver is in charge of receiving the signal from the remote control. The remote control, in this case for a car, a vehicle, an automobile, is gonna have steering and speed forward and reverse. Okay, so you can control those two features. If this was an airplane, you will have probably 3 or 4 channels because an airplane requires more levels of control. But for an RC car, we're gonna have 2 degrees of control, which are steering, left and right, and forward and reverse with different speeds. The receiver, we cannot see it here, but it's gonna look like this. This is basically a receiver. If you take a look, it's basically a piece of electronics with a crystal that is tuned to the frequency of the transmission. So we're using radio frequency. That's why this is called a radio transmitter. And then these are the outputs. The outputs are for 1 per channel, and 1 channel could be your speed, another channel could be your steering. And on a plane, it could be the aileron, the rudder, the thrust, and so on. So that's covering here. And what we're gonna see is that there are 2 cables, 2 3-pin cables going into the other 2 blocks. This is the RC servo, which is in charge of steering the front wheels. And this is the electronic speed controller, also known as an ESC. I'm going to talk a little bit more about this soon. But first, let me tell you that the RC servo, which is getting the instruction from the receiver, is basically going to move these wheels to one side or the other as you are commanding the direction with your wheel. And I have some tutorials on what are the signals used on my website ebldc.com. How do we deal with the PWM and such. That's what I call, by the way, RC PWM, which should not be confused with the PWM that we use to drive the motor, okay? The RC servo is in essence a motor with a little computer. This guy is closing the loop on position. So you're going to send it a command and it's going to go to that position and it's going to stay there. There is a bunch of gears inside and a bunch of control. So this is not a trivial piece of equipment. With that being said, the electronics that I'm going to replace on this car or neither the receiver, because I am not into RF. That's stuff that I really don't understand very well. That's not something that I can tackle yet, at least, or I'm not even interested. So that guy, that's something that I would just buy off the shelf. The RC servo, probably I could design my own, but to be honest, the amount of effort required to build your own RC servo is not trivial. You're gonna have to do a bunch of gearing and control loops. This guy's probably 10, 20, I doubt it's more than that, $30 if at the most. For me to build this, it's gonna cost me hundreds of dollars, and most likely it's not gonna work as well. So although I could develop one, there is no point for me in doing so. The one that I can tackle with so much ease, this is the stuff that I do every single day of my life, is the electronic speed control. So let's talk a little bit about this guy, because this is the important guy. The receiver is gonna send the control signal into the speed controller, and it's gonna command two things: the speed of the motor and the direction of rotation, if it's gonna go forward or if it's gonna go backwards. But also the intensity of the force that the motor is to generate, so that you can control the speed or the thrust. Let's say speed, because this is not an airplane. But there is one trick here. To control the speed of this motor, you're basically going to use an H-bridge. Okay, this is a brushed DC motor, but of course the latest in technology is the brushless. So for brush, we use a full H-bridge, and for brushless, for a three-phase brushless, we would use a three-phase inverter. Okay, so this guy can only do brush as it is. If I want to put brushless, I will need to change the whole thing. I'll tell you soon why that is important. The other aspect of this circuit has to do with this guy, which is the RC servo. The RC servo requires a lot of current. This is a motor here. This is not a virtual direction machine. This is literally a little motor that is moving a bunch of gears. It has to steer these wheels. The load is fairly considerable, so you're gonna need a lot of current to move this guy. That current will have to come from somewhere. The other problem is that the voltage that this guy uses is usually different than the voltage that the whole system uses. Let me talk about that. Here is the battery input. The battery could be anything from 4 volts to 40 something volts, 30 something volts maybe. So what's going to happen is that the electronic speed controller is going to use that voltage to drive the motor. But internally, there are some regulators that are used to generate the different voltages, like 5 volts, 3.3, 1.8, whatever you need to drive the electronic speed controller. What happens with the RC servo? The RC servo cannot operate with this kind of voltage. Let's say this is going to be a 9.6 volt battery. This RC servo cannot take that amount of voltage. So what we're going to do is we're going to use another piece of circuit inside of this, which is called the battery eliminator circuit. The battery eliminator circuit basically transforms the voltage from this connector, from the battery, into a voltage that this guy can use. In other words, from 9.6 volts to something like 5 volts. So that means that the circuit inside of this is going to have to do two things: drive the brush DC motor or the three-phase BLDC motor, and also power up the RC servo. And that energy is going to come through the control signal, through the receiver, and into the RC servo. Okay, so these two blocks are going to have to be inside of this. All of that is important. I'm going to show you why when I tell you about the circuit that I have implemented to replace this guy. If you have tuned into my YouTube channel, you will know that I have been working on something I call PowerPACk. PowerPACk, because it's in essence a system with two boards that when you put together forms a pack like this. So this is a PowerPACk. It's a pack of power. However, the other funny aspect of the name is that there is a chip inside of as part of the system that is called the Power Application Controller, which is this guy right here. So it's a PowerPACk because it's a pack and because it has a pack. If you have seen the video where I show what you can do with these guys, you will know that I was driving basically a three-phase BLDC motor with these guys. It's basically because this chip was designed to drive three-phase BLDC motors, or PMSM motors, either way. However, there is nothing prohibiting us from doing an H-bridge. So you could do brush DC motors, 3-phase BLDC, 3-phase PMSM, and I bet you could even do a stepper if you want to get get your hands dirty with some other technology. Here is an example of how you can drive a brush DC motor. I just basically never populated this half leg of the H-bridge, so of the 3-phase inverter. So now it's just a full H-bridge. That's a way of doing it. However, I went ahead and I designed a board that is just an H-bridge. So that way it's you don't have to worry about whether you populate or not. I also added parallel FETs in case you want more current, but these are fairly low RDSN FETs, so you can do some serious currents with these guys. The concept behind the PowerPACk is that you can mix and match. You could say, well, I want to do a brushless today. Well, let's put a brushless muzzle. Or I want to do a brush. Well, let's put a brush H-bridge. Also, I have different controllers. Now, I call the controllers the brain because that's where the pack device is, and that's the brains of the operation. And here are two examples of different brains. This guy is a buck converter, so we can do 36 volts if you want it, maybe 48. Really, the highest voltage that the PowerPACk 5223 is going to take is 72 volts, so I wouldn't go past 48 if I were you. 36 is good because it gives you 2x. But for example, this is a different topology, exact same chip, okay? Exact same chip. It can do buck boost, so it can work down to something like 3 volts. You still need to power up at 8, but if the voltage drops or droops below 8, this guy will be alive. And that is important because you want to squeeze that input as much as possible to continue with your operation. Now, these two boards that I had designed last year, all they have is the circuitry to drive the 3-phase BLDC motor. And as you know, we cannot complete the RC car project with just this, because although I can drive the motor for forward and reverse, I cannot drive the RC servo. I need the second block, which is the battery eliminator circuit. So I redesigned the application and I added the battery eliminator circuit down here. The board is a little bit bigger than the other one if you look at the size, but that is how it works. Now you get all that you need to drive both aspects of the RC car, both the H-bridge or the 3-phase inverter, as well as the RC servo. So this guy powers up everything. And the beauty is that if you want to do brush, you just put your brush muzzle board. I call it muzzle because that's where the juice is. This is basically the power stage, okay? But if you want to do brushless, then you put brushless. Exact same brain board can do either. In fact, I bet I can put the firmware, okay, the code to do either, and it could basically, you could just connect whichever motor you want, and then it just goes. So that's the beauty of being able to design your own board and your own power stages, is that you can basically tailor to your needs. So I created a little 3D printed enclosure here to put the board, taking advantage of the holes, of the existing holes. I don't want this guy rattling a lot. Now be aware that's probably not going to work very well if you got a muddy situations of water. I mean, when you look at the Traxxas offering, they are enclosed, they are waterproof. So this will, I would need to work a little bit further into making it waterproof. First thing you're going to notice when you power it up is that the red LED is blinking. Right now the system is disabled because the RC receiver connection has not been made. So when I power my guy, now it goes green. I don't know if you can see that, but it went from blinking at red to green. So now I can steer the car. So the battery eliminator circuit is providing 5 volts through the receiver, so it's also powering the receiver and is powering the RC servo. The battery is going to power this motor and everything else. Now the PowerPACk 5223, it has all of the circuitry that you need to power up the system, except for the power required to power the RC servo. So I need that from this block. But all of the rails, all of the circuitry in terms of pre-drive stage, analog, ADC, differential amplifiers, comparators, everything. Linear rails, 3.3, 5 volts, 1.8, everything is inside of that little chip in there. So that guy is going to control this motor like this. And it is going to basically power the system and the motor. But you know, all of this is fantastic. How about we take it for a spin? Okay, let me show you a little bit of what I can do here, because I coded this differently than your typical RC car ESC. And what I'm trying to do here is just control the speed and the direction of rotation, so I can go forward, I can go backwards. But if you recall from your typical RC car, you hardly ever can do this. And the reason is that for whatever reason, and I think this is a mode of operation of typical ESCs, you want to go forward and then you want to go through a sequence to be able to go backwards. It's like you have to go backwards twice so that the car actually goes backwards. At least that's how that was the default mode that this ESC came. I haven't programmed any of those modes, so all I can do is go forward, go backward, and immediately. So I can control the braking immediately by just playing with the trigger. Obviously, I'm still not a good driver. Blasted, man. I busted the bloody car. Oh well, what can I do? You know, this is just the name of the game. This stuff happens. These parts all break and you can replace them. So that's the name of the game. A little disheartening because obviously now I cannot continue my race. But at the same time, this is fantastic news because I literally exceeded the I basically pushed the car to exceed the limits. I broke it, but the electronics are in perfect shape. That is good news indeed. I am pleased. But because this part is broken, now I gotta go back to Hobby Town. So I'm wondering if my wife needs to go to the Burlington factory. Well, as I get ready to finish this video, there are a few things that I want to point out. On this module, the what I call the PowerPACk ESC with battery eliminator circuit, I am using the CEPIC configuration, that is the buck boost. And why that is important is because it allows the microcontroller to remain alive even if the battery voltage drops below a significant level. In this module, I need to wake up at 8 volts, which is okay because the battery that I'm using is 9.6 volts. However, in the event that there is heavy current usage, causing the battery voltage to collapse dramatically to a voltage such as, I don't know, 4, 5, or even 3 volts, the microcontroller will remain alive. Not only that, the microcontroller and the system are going to see 12 volts, which is what I use to drive my gates. That is important because you want to you want to maintain efficiency on the system. If the gate drive voltage were to decrease, now your FETs would not be fully powered and you would not be able to turn them on. Now anybody could argue, but if my battery is so low, then of course the motor is not seeing a lot of power anyway. But you will be amazed. I mean, there is a lot of current going on, so the power is practically there. This only happens for you know, maybe microseconds, milliseconds if at the most, only if the load is really high. So there is still a lot of power on the system. And what this CEPIC, the buck boost configuration, allows us is basically two things. It keeps the microcontroller alive but also it keeps the gauge drive at a healthy level. Well, I think this has been a smashing success. I mean, hardly ever do I get a project that works so well from the first time. Not that this is the first time that I design a motor controller. I mean, this is basically, as I said before, this is what I do every single day of my life. So this is something that I have done so many times that this is just it's a different flavor. It's the same popsicle with a different, what do you call it, the different stick. I want to thank you for watching my YouTube video. Feel free to stay tuned. I'll continue doing motorific projects in the weeks to come. So I'm going to see you in the next time.